Okay, so my last video ended due to complications, but we're just gonna resume it from the last video. So going back to it, we're doing a numbering system where it's 1, 2, 3, 4. But we know that 1 is where the first branch is at. So since we know this is a cyclo, and this is the branch right here, this is going to be cyclo. And then our ending, well, we have 4, so we know that it's going to be but, and then ane, of course. So now to find the one at the first branch, it is at number 1. So we know that it starts at 1. And since bromine is a halogen, that ends in O. So it's going to be 1 bromo. So the full name for this is 1 bromo cyclobutane. All right. Now we need this the second out of the 4 where n equals 3. So this is the same thing, C4H7Br. This time we're going to do a triangle, right? That each dot represents carbon, of course. And we'll put bromine over here. So we know that this ends up with 3 hydrogens. This one ends up with 3 hydrogens. This one ends up with 1, so that's 3, 4, 5, 6, and then this is the last one, 7. So that we have 7 hydrogens, 1 bromine, 4 carbons, as we need to have. We circle the cyclo, so we know that this is the cyclo. Well, it's actually its number. Let's start this number first. So we have 1, 2, 3. So we have cyclo, and since it's 3, it's going to be propane, propane as the ending. So we have a branch at 1 and a branch at 2. Now the branch at 1 is bromine, so again halogen, just bromo. And then the branch at 2 is just methyl because it's just 1 carbon and 1 is just methyl. So if we put all this together in alphabetical order, we have 1 bromo, 2 methyl, cyclopropane. And that's it for the that's the name for the second one. We can tell these are different, so they are different constitutional isomers. Next, we have the third one, same thing, and we're going to be doing a triangle again. So C4H7Br. So we got the triangle. Oh, but this time, this is going to be the complicate substituent where this one right here, it will go to another carbon, and that carbon will go to the bromine. So same thing here, we find that this is a triangle, so we know it's cyclopropane as well, the same as last. Now this is where it gets a little bit tricky. So let's number them first. Lowest number goes to the first branch. So this is our branch right here. So we have 1. It starts at 1 and it goes right here. So we know that that's 1. We know that our ending is going to be methyl because it's 1 carbon. So we'll put that at the end. That's 1, and this is bromo, as indicated by the halogen. So we got 1 bromomethyl. Now, since all of this occurs at the first number, we know that this is going to be 1 again, 1 bromomethyl cyclopropane. And this is a different name than the other 2, so we know that's a different constitutional isomer. Now to go to the fourth one, which is going to be where n is equal to 2. This one, we're also going to have the triangle. But this time, we're going to make carbon over here, going down, and bromine on this side. Now, we know that it's a triangle, so we know that it's cyclopropane again. So, now let's number them. So this is 1, 2, 3. We have 2 branches at 1. So the 1 is at bromine, which is just bromo because it's a halogen again. And then we have 1 at just the regular, let's actually circle. These are our branches. And this one is at methyl because 1 is methyl. So if we were to put all this together, that is 1 bromo. Wait a second. 1 bromo, 1 methyl cyclopropane. And those are all 4 constitutional isomers for number 2. Next, we are going to go to number 3. Now, number 3 is asking us to show that phenol is more acidic than cyclohexanol or vice versa. So the first thing we want to do, of course, is find the conjugate base. So of each of them. So this is phenol, this is cyclohexanol. We want to find the conjugate base of each, which we want to get rid of the hydrogens, and of course that will get a negative charge. So this is going to be like that. That's a horrible hexagon, but yeah, it's a hexagon. We get that. Let's draw it the same. Going to be doing O, and since we're removing the hydrogen, we're going to give it 6 lone pairs and the same hydrogen, the negative charge. Same thing over here. Except we don't have double bonds throughout it. And this is going to be that's the OH again. Sorry, the hydrogen will get removed, making it like that. So we have it as a negative charge. So first we need to find the size of the negative charge, where we have the negative charge. So we have the size. They're both O versus oxygen, no difference. Next, we have the electronegativity of the atom itself, and again, O versus O. So that's just going to be not available. I'm putting that for there's no difference. Next, we have electronegativity of the neighboring atoms, and this is going to be, again, they both bond with carbon, so it's just going to be carbon versus carbon, which there's also no difference. So this means we have to do resonance. Yay! So we can already tell, based on it, that cyclohexanol has no double bond. So to do resonance, you have to have a lone pair. Then you need to have a lone pair, single bond, then a double bond. So actually erased that. I just told you guys. So yeah, we have a lone pair and then a double bond as well. So since this one has lone pairs, but it doesn't have any double bonds, we know that this is gonna have no resonance. This one has double bonds, so we know that it is gonna have resonance. But we're just going to do that. We're gonna do the resonance. We have to display all of them. So for the resonance for this one. So we start out with the conjugate base of it. So let's actually write it out a little bit bigger so that it looks nicer or better. 1, 2, 3, 4, 5, 6. So we want to, we forgot the double bonds. So we want to circle the double bond, the lone pair, put it right here. Circle this double bond, put it right here. And that's going to give us lots of hexagons. So with this this one is going to move in. This is going to turn into a double bond, oxygen with only 2 lone pairs. It's no longer going to have negative charge because we got to put that. This double bond turned into a lone pair up here, which gave this a negative charge. Next, we have to move this negative charge, so we're going to have to put that right there. And then we're going to circle the double bond and put it on that. Yeah, on this one. Now, after it's being done, we know that we're gonna have. That's horrible. So we know that this no longer has double bond. Double bond is right here. But this double bond is going to turn into a lone pair right here, giving this one the negative charge. So we still have the double bond right there. So now we're going to be doing our fourth one. So we got 1, 2. This is our third one. We're going to go to our fourth one, making this double bond right there. And then with this, that lone pair, we're going to put it right there. And this double bond, we're going to put it right here. So after I guess this is going to show the resonance cells because I ran out of space to go to the side. We're going to have, so still a double bond right here, double bond oxygen with the 2 lone pairs. This one is going to have the double bond, and right here will be the lone pair with the negative sign. That's our 4th one, and we have one final one. This lone pair will go to this single bond, and then this double bond will go right back to the oxygen. We just end up where we came from, but not necessarily because it still looks different. So after resonance, we have it like, gosh, it's a horrible hexagon. I'm just gonna redraw that because. So we know we have a double bond right here, double bond right here, and since we moved this to a double bond, to have that right there, this is gonna turn to a single bond with oxygen back to 3 lone pairs, 6 dots. And these are all the resonance structures that we have for phenol. As we know, cyclohexanol has zero resonance structures because it has no double bonds. So now to explain it, so because phenol's conjugate base has more resonance structures, it has 5, then the negative charge is actually more spread out throughout the Lewis structures. This means that it is more stable. Because it is more stable, it is more acidic. And since the conjugate base is more stable, phenol is more acidic, which means that we prove that phenol is more acidic than cyclohexanol. All right, now on to question number 4, the last question. All right, so we're actually going to be doing these 2. So we need to draw 2 different trisubcyclohexanes. We have them right here. I drew them, and we need to show which is the most stable conformer, however you say that. So with this one, of course, we're going to be doing the chairs and flipped. So for the first step, we know that we have to draw the chair flips, of course, and the largest or most groups on equatorial is of course the most stable one. So let's do the first one. We're gonna do this one to begin with. So we know we have the chair. Let's actually draw the chair. Oh my gosh. So we have it like this. All right, so we'll number it 1, 2, 3, 4, 5, 6. All right, so we know that this goes down, up. This is going to be the opposite, up, down, down, up, down, down, up. So right here at 2, we know that this one is the same thing right here because whenever we numbered it, oh, I forgot to number it. So we do 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Lowest number going to the smallest branch, and each branch has to have the lowest numbers. All right, so this one is going to number 2. We know that number 2 is CH3, 3, 3. That's a big one. Wow. All right, so at number 1 right here, going down, we have CH3, 3. We have hydrogen over here, CH3 over here. Now, based on what we can see, we can actually see that we have 3 axial and 0 equatorial based on the way the chair looks. Now, of course, we have the chair one side. Now we need to flip the chair. So let's flip the chair to go like this. These chairs are horrible. It's probably not big enough in the center, but it's fine. So keep the numbering the same. 1, 2, 3, 4, 5, 6. All right. So now this number 1, it will actually go H. This is H, and it's actually going to go up. And Right here we have the CCH3, 3. Down, hydrogen, side. It's actually supposed to be side, sorry, this is supposed to be up. So we know it goes like that. And that's the big one, CH3, 3, 3. All right. Now over here we have the H and the CH3. All right, and based on the way how we're looking at this, how we're looking at it right here, we have 0 axial and 3 equatorial. Now, since we don't care about size right now because they're about the same, but since this one has more equatorial, it has 3 over 0, this is actually the most stable of the two flips. Of the two of the same. Next, we're gonna move on to the second substance that we have, the second tricyclohexane. So this one is actually going to be drawn in, let's see, oh, this is horrible. Same thing. All right, same numbering system, of course. 1, 2, 3, 4, 5, 6. We have this CH3 and down based on the numbering system that we provided above. This is an H. This is an H. This goes up, and that's also a CH3. The 6 right here goes up. 3 goes down. 4 goes up, side down, and this is the big one. It's gonna be C. CH3, 3, 3, and right here at 5 it goes down. So based on all the axial and equatorial, we actually have 2 axial and 1 equatorial. All right, now let's do the chair. Oh, I forgot to write for this one I forgot to write the chair flip sign. And same thing over here, chair flip sign. So we're about to flip the chair. So to do this, we have to write the flip chair, and let's actually write it hopefully better or decent, like lightning bolt, nice. So we have 1, 2, 3, 4, same way to number it. So right here we actually have hydrogen going up and CH3 going to the bottom, CH3 going up again, and then hydrogen going bottom. It's horrible. Hydrogen going bottom. At the same time, we're just gonna skip to this part. Hydrogen going to the side, and the big one, CH3, 3, 3. It's horrible, but yeah, it's just a bigger number. At 5, and nothing, since we don't need to worry about that. And over here, we actually have 1 axial and 2 equatorial. Now, even though there's more equatorial on this one actually has a bigger number, and as we know, the larger the number, it's actually winning. So this is actually this one before the chair flip is actually going to be the most stable. All right, because the larger, because even though this one has more equatorial, the larger atom over here at equatorial is the atom over here at equatorial is actually larger than the one at the chair flip. Now to find the most stable between the two trisubcyclohexanes, we actually have to compare these two. So this one has a large how do you say it? Sorry, the large substance, which is a CH333. How do you say that? It's both larger, and it wins E-wise, like equatorial wise, but then it's before chair flip. This one is only larger than its chair flip counterpart. Now, since this one is both larger and most equatorial, and this one is just most equatorial, that makes the first one our most stable trisubcyclohexane. So going back up here, this will be our most stable. All right, now that completes the extra credit for this assignment. Thank you. and have a good night.